what similarity transformation, classes, and what conjugate elements, right? These three terms we need to introduce. Um, and then we took some example for C3V, and then worked out at least for one example. I think we worked out similarity transformation. Um, Remaining, I think I asked you to do the sigma v planes, all the planes, um, to prove it, show that all three sigma v planes form a class, right? If I remember, yeah, that's what I've given one. Other one was write the matrix representation of the BCl3 molecule. You remember the BCl3 molecule is point group is D3H. D3H. So it will have different matrix form. Matrix, if you perform it, it will be different. So have you tried it? D3H. One of you or two people, I think, sent it by email. Yeah, I mean, I didn't see completely, but it's fine. I think somebody tried. Others also trying D3H point group. So D3H is BCl3. So you consider the atoms, the bonds, the three vectors. You can say these three vectors you consider as basis, and then you can write the matrix, a 3 by 3 matrix. So E will be 1 0 0 0 1 0 0 0 1. Before that, D3H has what? Has E, C3, C2. Sigma H it has in 3C2. Yeah, C3, 3C2, sigma H. Since you have C3 and sigma H, you have S3 also, followed by sigma V planes. There will be 3 sigma V planes. We agree with this. There are 2 C3s. So this will be C3 and C32. So we can write 2 times of this one. So these are the symmetry elements present in BCl3 molecule. So you can write all these operations in matrix form. That's what I have given in last class, the homework. So anyone tried other than a couple of people? Yes or no? So how do we make it full? Yeah, so if you don't want to speak, you can chat also. I think you just give your comments in the chat box. Have you done it, some of you?
So can you show the 2C3, please?
Sorry?
2C3, so how BCl3 contain 2C3?
Okay, so fine. Okay, so this is new for you guys. So maybe I'll work it out. Okay, then you can try it for some of the molecules. So E at least you can understand, right? So this is there are 3 axes. So we are following these 3 bonds as the vectors. Atom position we are following. Okay, this is Cl, this is Cl, and this is Cl. Okay. So we are going to follow the atom position. So in E symmetry, the atoms are all in the same place. So we can write 1 0 0 0 1 0 0 0 1. So this is, you can say this is x-axis, y-axis, z-axis. In that way we are doing it. And then let's try for C3. Let's just C3. So C3 is 120 degrees. So I call it as CLA, CLB, CLC. Okay. So if you rotate it, axis is C3 axis is clockwise, right? C3, which is say this is a planar molecule. You are placing this molecule BCl3 on this board, and then the axis C3 axis is across. I mean, you go from this side to the other side of the board. So that is C3 axis. And then there are three C2 axes. So this is perpendicular to the C3. So this is C3 means C2 you have here, this side, and this side. So we'll come to C2 later. But for C3, you consider here, and then we are rotating by 120 degrees. So if you rotate it, what happens? So this will go to B, Cl, Cl, Cl. This will become C time, A time, B time. If you rotate it by 120 degrees, the atom's position will be interchanged. CLA will go to the CLB, CLB will go to the CLC, CLC will come to CLA. Okay, so we'll stick to the CLA. CLA shifting by 120 degrees, it goes to the CLB position. So here, this is original one, but that will be shifted by next position. So I just go to the B position. So the first atom gets shifted to the B position, and then actually the atom should be here, but because of rotation, it has gone to the next position, shifted by 120 degrees. The B atom and C atom, from here, it was originally here, it has come down to the first place here. So we can write something like this. So this is for C3. And similarly, C32 will be 2 times rotation, right? So from here, you can write C32. 0, 0, 1, 1, 0, 0, then 0, 1, 0. So the matrix form can be written for C32 in this fashion. Yeah, I hope it is visible. Huh? So this is now we have written for VE and C3 and C32. Let's write it for the easier one is sigma H. Because sigma H is we are going to place the molecule, the plane on the plane of this board. So we can simply write. So if you place the mirror plane parallel to this board, so atom position will be at the same place. It will not interchange. So sigma H, it is also equal to sigma H. E is also equal to sigma H. Okay. If you place a mirror on this plane, on this board, the atom position will not be shifting. So it is same as the original place. So this is the original matrix form, and there is no change. So it will be sigma H is same as this one. Okay, and S3 also we can write. S3 is what? C3 followed by sigma H. Right? S3 means nothing but C3 followed by C3 and then sigma H. So there are two operations involved, C3 and sigma H. So when you perform C3, you got this matrix, and then after this, you are going to perform sigma H. So it is not going to change. If you perform sigma H, you are going to place it on top of it. So this is also equivalent to S3. Okay. So I'm just completing the easier one. Now,
sir,
erase it. Yes, yes.
Sir, this molecule will not contain S3, sir.
This will not have S3.
No, sir. Can you check once? I don't think it will have S3.
S3, why it will not have?
No, sir, it will have.
It will have, no? It has C3 and sigma H.
It will have.
It will have S3.
So can you show it once, sir? So can you show it?
This is a molecule, right? So this is a molecule. It has C3 rotation. So if you rotate it, it goes to this place, and then place a mirror again on top of it. So the molecule you are going to re-get it. So S3 means what? C3 followed by sigma H. Yeah. C3 it has It's very clear. If you rotate it by 120 degrees, the atom position will be interchanged, just shifted by 120 degrees. So this is done, and after that you are going to perform sigma h. You are going to place the mirror on top of this molecule. No? So atoms will be placed there itself. It's not going to change. So this is having S3 also.
Oh, okay,
Most of the
okay,
planar
sir.
molecule do have.
Okay, sir, I got it. I was thinking that the chlorines were different. Okay, sir.
It does, it does. So that's why I wrote C3 equal to, in this case, it is C3 equal to S3, the matrix form. So I'll erase it and let's work it out other remaining. This is also done. Okay, this is also done. So C2, no? If you perform C2, so there are too many noises, right? I'm sorry about that. So from home, yeah, it will be like this. So our apartment is close to airport landing site. So there will be quite often there is always landing or takeoff. Because of that, all these car alarms go on. So let's come back. C2. If you perform C2, which is perpendicular to C3. At C3, we found out something like this, perpendicular. So C2 is, it could be like this. C2. And then the second C2 is like this. And third one is like this. So there are three C2s. I just call it as 1, 2, 3. Prime, double prime, triple prime, whichever way you can write. C2 1. So I'm just placing on top of this one through E. You can say why you complicate. Just work out with just only one C2. So I'm placing over this place on CLA. When you do that, so what happens? These two will be interchanged. This two, CLB and CLC will be interchanged. So B will become, and then CLC will become, whereas CLA will remain as such. So this can be written as in matrix form. A will remain as such. B and C, its position will be interchanged. So this is 0. B will go here, 0, 1, 0. Okay, so this position will be interchanged. This is C2, 1. Similarly, other two you can write. Say C2 double prime, you can say. C2 double prime just placing over CLB. So if you do that, CLB will remain as such from the original position. So this is going to be same. And then CLA will be interchanging to CLC. This will go this way. Okay? So A will become here, and CL will become, C will be somewhere here. So it will be something like this. Cl double prime, which is passing through the CLB atom, and then Cl C2 triple prime, you can say. Triple prime is say over the C atom. So if you place it a mirror top of it, what happens? So these two will be interchanged. A and B will be interchanged. So when we interchange A and B, get something like this. C will remain as such. So these are the symmetry elements. C. Okay, it's plane, or you can say it's a rotation also. So the atom is going to be same. C2 triple prime. So you'll get something like this. You agree with this? There are 3 C2s, which is similar as sigma V also. Sigma V is also, you will place it over the um, one boron and one chlorine atom, right? So the same atom going to, this is also equivalent to sigma V prime. This is also equivalent to sigma V double prime, and this is also equivalent to sigma V triple prime. So you'll have matrix form, same for sigma V prime and C2 prime, and C2 double prime and sigma V triple double prime, and again for C2 triple prime and sigma V triple prime. So you'll have different matrices, but some are same type. So like this, one can find out. And in addition, what is the trace of a matrix?
Summation of all diagonal elements.
All diagonal elements, right? So here we add it up here. Okay, here it's all diagonal elements. If you sum it up, we call it as a trace. So for identity, it is trace is 3. We write something like this. We use a symbol called chi. That's a trace of a matrix. So we write it 3 here for E. And for C2, it is chi of C2 is 1. It's a 1 for every C2. You can see here also. All C2s will have 1. Similarly, you can have it for C3. C3, it was coming all 0. To check it, I erased it, but the C3 it was all, because you are rotating, right? All 3 atoms got interchanged, so it is a its diagonal elements are all 0. So one can find out the diagonal elements, the trace, and then you can write it. Okay, so in this way you can write. We'll come to this why we need the trace when we talk about representation.
Sir?
Yes.
Sir, trace of, I want to know about the trace of the planes. The sigma V, it will be 1, and for the sigma H will also have 1, or it will have something else?
The trace.
Yes, sir.
I forgot.
Because I think all
right?
the planes have 1. The trace of all the planes is 1.
Sigma H will be 3. This is equivalent to sigma H, right? So E is equivalent to sigma H. So it has a trace of 3.
So
Chi of E is 3. Chi of sigma H is also 3. Because sigma is we are just placing a mirror on top of the atom. So we have considered 3 vectors, 3 bonds, BCl bonds as a representation. So those are not changing, right? By placing the sigma H plane. So that's why the matrix elements are all same. Like all the diagonal elements are all present. So when you sum it up, the trace is 3 for sigma H.
Okay, sir.
I hope.
Sir,
yeah.
Sir, for the C3, when we did that rotations and converted that 2 cos theta plus 1 that we came out of the formula for Cn. And the similar thing that when we do for Sn, it is 2 cos theta minus 1, right?
Yes. Yeah.
And for if we do that, then the trace of S3 comes out to be minus 2.
Yes, it will be different. Yes, yeah.
Yes,
but we are taking the vectors, the Cartesian coordinates as basis.
Yes, sir. Yes, sir. Yes, sir.
Then
Cartesian coordinates
cos theta minus sin theta 0. That will be the representation.
So we can choose basis according to our need, right? Rather the Cartesian coordinates or the molecules as the basis.
Yeah. So the basis we can choose it based on which problem we are going to address. Say if you want to study molecular vibrations, then we choose the bonds. Here the BCl3 bonds we are concerned, no? So that we consider, and then see this representation. If we are looking at pi orbitals, then we take the px, py, pz orbitals as a basis. And if you are studying the metal complexes, particularly the transition metal complexes, then the d orbitals comes into picture. So we take the d orbital shapes and then write the matrix. So the matrix form can be different type for the given molecule. So it depends on which problem you are trying to address. If we are interested in studying the IR vibrations or Raman, then we go for vibrational modes, which for BCl3 we just wrote. And then if we are looking for pi orbitals, aromatic compounds, the syn anti-conformation of pi orbitals, like for photochemical reaction, syn, the pericyclic reactions, right? We can consider the pi lobes, right? So for that, the orbital lobes will be considered. So so it depends on the problem in hand, like which problem we are trying to address. Based on that, the basis will be chosen. So it will be different for given molecule itself. Same, we can consider different bases. Okay, so it will be
Okay,
varying.
sir.
If even here
Thank
we
you,
have
sir.
only bonds, but if you're considering the Cartesian coordinates as a basis, then you can write in terms of cos theta minus sin theta for rotations, for C3 rotation and C2 rotation. We can write the rotation matrix, the cos theta minus sin theta 0, like that we can write.
But sir, in that case, the trace will be different, right?
Yeah, it will be different. Trace will be different for different representation. Yes, but when you you see, we will generate a character table, and then we multiply with these trace elements with the characters of the character table, and then we do certain procedure called as projection operator. We use some projection operator to uh, annihilate certain operations. We'll come to that shortly, but till now, you can write the operations in different matrices, considering the either the Cartesian coordinates or the bond vectors or pi orbitals as a basis. Okay, so your trace element will be different for every matrix.
Okay,
Um,
okay,
then
sir.
how we are going to apply this, we'll see, because we'll use this basis for different purposes. Um, um, for that, we can write different matrices. Here also we consider only 3 atoms, right? 3 by 3 matrix. So if you are considering the 4 atoms, but there are 4 atoms in this BCl3. If you consider boron also has a pi orbital. Say you are considering the what is happening here. So boron has p orbital also, right? So if you consider p orbital of boron, say we are considering the p orbital of boron, and then chlorine also has p orbital, uh, p orbital, p orbital. So when you consider the p orbitals of these elements, then there will be 4 p orbitals, right? So to know the bonding between these bonds, so you will write same matrix in 4 by 4 matrix. 0, 1, 0, 0, 0, 0. So now we are considering the p orbitals present in these atoms, and we want to know the bonding so between boron and chlorine. What type of bonding is present, and then what orbitals are involved, either px or py or pz, or combination of px and py, because p orbitals could be 3, right? One is on this plane, so you consider this is as x, this is as y, and the other one is coming z. So there are 3 axes, so you have px, py, pz. Which bond is formed, which orbitals are involved in this BCl bond, one can find out considering the orbitals, px, py, pz orbitals of chlorine and boron. And the chlorine, of course, s orbital is irrelevant here, because s orbital is present in this also, both chlorine also and boron also. So it automatically comes s orbital. But the bonding, if you want to know which bonds are involved, so we use pi orbitals. When you take pi orbitals, there are 4 pi orbitals. So the matrix of course becomes 4 by 4 matrix. For each pi orbital, you write 1 row, and then it becomes 4 by 4. Okay, so just to, if you want to know the IR vibrations only, then you choose the bond vectors. If you want to know bonding, which bonds are involved, either px or py or pz are involved, then you look at the pi orbitals of each atom. So then the matrix form is different. Now the character of is 4. Okay, so we'll use this in going from reducible representation to irreducible representation. So in this case, it is 4 because we added up all the diagonal elements. Like that. I just gave an example. We are going to see this thing in detail. Okay. Then we'll go to the actual application in very few weeks' time, maybe, or just within a week's time. Then you'll appreciate it better why we are learning all these things. But at least we are introducing to various tools available to reach that stage. Okay, so this is clear. So I can go to the next topic. Robin, you have any question?
No, sir.
Sir, what about S32, S33, and S34 and S35?
Can you repeat? I don't know what is the problem. My mic is not working properly. Can you please repeat what you said?
So in BCL3, what about S32, S33, S34, and S35?
S3, this is atom. So S is the sulfur atom.
No, sir, operation. S3 axis. S32, S33.
S3.
Yes, sir.
Yeah, that will be different matter for this molecule. S3 operation, right? So basically it is C3 into sigma H. So if you perform C3, you'll have 4x4 matrix.
I told for BCL3 molecule.
BCL3 only, right? You are looking at BCL3
Yes.
and then
Yes.
you want to find out C3, right? You can do that. So X is here, Y is here. So if you are looking at the orbitals, you are showing the orbital shapes. Huh? You can say we are just considering the X orbital. So plus, 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 minus, minus, minus. Here also we take boron. Plus orbital. So I'm just taking the px orbital. Okay, I want to find out. We can combine. We can take all three px, py, pz. But let's start with px orbital. Px is of each atom we take. Say ex of this one is 1, and then px. If you rotate it, what happens? So you can find out. Or simple one to begin with, pz we take. Okay, pz orbital. So which is coming out of the board. So all the positive lobes of pi orbitals are towards us, and negative are behind the board. Okay, so this is all this BCL3 is planar, whereas the orbitals are located perpendicular to that. Okay? PZ orbital. So let's start with PZ. So if you do that, what happens? C3 we can write. Let's see for C3. So if you rotate C3, what happens? So this is for boron is not going to change anything. So it will remain as such, whereas this will go to here, this will go to here. So the location will be shifted. 0, 0, 0, and if you rotate it, this will again called as A, B, C. So,
Sir, I told for simple BCL3 molecule, not including the p axis.
sorry?
For simple BCL3 molecule.
For simple BCL3 molecule, I wrote no S3.
Yes, sir. I want to know the S32 and S33 about that.
You want to know what?
S32, S33.
S3 operation, right?
Yes, S3 and S32, S33, S34 and S35.
S34, S35, what is that? I didn't understand.
S34 is C34 into sigma to the power 4 like C32. We also have na S32, S33.
No, yes. Can you type? I didn't get yes, 4, yes, 4.
Like say C3, we also have na C32. So for S3, we also have S32, S33, and S34 and S35.
S34, S35, no. You mean this S4?
No, sir, S4. No.
No, can you type? I am not understanding your question. Can you please type in the chat box?
So I want to say for one C3 axis, the dependent operation generated is 2, C3 and C3 2.
Yeah.
And for S3, the dependent type of operation is generated as, if we consider 6, and one is E, and another is S3, S32, S33, S34, and S35. So these also be group element, na?
No, I'm not getting what you're saying. Somehow, I'm not understanding your question. I will go to the next topic, but meanwhile, can you please type in the chat box? Okay.
Okay.
Yeah, please type it. I'll address it. Yes. Before I'll just go to the next topic, but I'll address your question. So yesterday we were talking about classes, right? So there are some rules of class. So yesterday we saw there is a definition of class. It's a complete set of elements which are conjugate to one another. It's called a class of a group. And the rules, there are at least 3 rules. One is in a group, every element is conjugate of itself. Every element is a conjugate of itself, because in a group there is always identity present. Okay, so every element is this is because of E is present. Say you have E, A, B, C. Then how do you do that? To find out class, you operate with A, E inverse, you can say, and then E will always give A. Okay, so this is one, and then again E inverse B, E will give B. If you have the element C, so if you consider C, C inverse, no, E inverse C, E will give always C. So every element is conjugate of itself. Okay. Earlier yesterday I was writing A. If you operate with E and E inverse, it will give, or not E. If you have any other element, if you multiply with X or X inverse, it was giving B, right? So here one of the first rule is every element is a conjugate of itself, because E is always present. So you can write in this form. Okay, so this is the first rule. Second rule is change the pen. Yeah. So if A is a conjugate of B, say in a group, if A is a conjugate of B, then B should be the conjugate of A, because both A and B are in the same group. So you can write B, then A. What it means is if you have X inverse A, X, it will give B. Okay, so this we saw yesterday. Similar transformation effort to perform. So by this rule, if we do the inverse, if you take the inverse, so this will become B, X, X inverse A. So if you do the other way, then you will result in, you can find out the similar transformation of B, and you will get A. Whereas if you perform the similar transformation of A, you will get B. That's second rule. Okay. Third rule is if A is a conjugate of B and B is a conjugate of C, then A, B, C are mutually conjugate. Okay, so that's the third rule. So if A is a conjugate of B and B is a conjugate of C, and all A, B, C are the same group, okay, then A, B, C are called as mutually conjugate. So that's the third rule. I mean, I don't have to tell much about this because if A is giving B and then B is giving C, say A X inverse B, then B is X inverse C, and then if you these two are valid, then you will get C also. So you can say C. You get A. So it can be mutually conjugate. It can come like this. That's what it means. So these two are mutually, all three are mutually conjugate. If all three are present in the same group. So these three are called as a class. ABC will form a class. So these are three rules of a class, which we apply in our further study. Class is done. Let's go to matrix form. Okay, so yesterday I think we started with the diagonal matrix, right? Let me see what question he has posed. S3 into 2, S3 into 3, S3 into 4, S3 into 5. Power. Okay. So, Ajit Gosal, there cannot be so many S3s. How many S3s possible? Only 2 S3 possible. S3 and S32. So, because you have C3 and C32 for D3H, right? This is for D3H, you have C3 and C32. So that could be S3 and S32 only. It cannot be beyond that. So did I answer? Yes. 3 and S3.
So for Sn, if n is odd, the total number of operations generated is 2n. So for S3, total number of operations generated by S3 axis is 6, na?
I don't know. You type it. I'm not understanding your language. Okay. Total number of operator generated. What I didn't understand. Others could follow his wordings, his statement. Anyone? Robin or those who have studied already group theory. Anybody could follow?
Sir, he is saying if in Sn n is odd, then the operation from this Sn should be 2n. Like in S3, it should be 6 operations. That is what he is saying.
Okay, S3 can have S6, huh? For odd, huh? So for odd number, yeah, there is a definition. I mean, there is for even and odd, there could be multiple, but in this case, it's not there. So much is not there. I don't know.
Yes, sir. Excuse me, sir.
Yes, go ahead.
So because S35, if we apply the operation, it is equal to S32 only.
Yes,
And
it is S32 only, right?
Yes, and S34 is equal to S31 only. C31 only.
S34 is S31, yes, and S35 is S32.
Yes, sir. And S33 will go for like sigma only.
E.
So I mean, there
S32
are
will become E, I think, right? Or
Yes, sir. Yes, sir.
Yeah,
No,
so
that
E.
this.
So it's a
So there will
multiple
be
he has written. It's only
sigma.
yeah. So
Yes, sir. There will be like we do operate it for like 6 times, but those 6 operations come out to be like already that we have like obtained, na? So like that.
it should be n minus 1 operation for Sn, n equal to odd. Yes, that's it. Yes, yeah. Even if it is more, it will be equivalent to what is already present. Yeah. You think about it. I don't know. I mean, I'll search why you are getting S3 6 and all, S3 5 and all. I don't know. Okay, Arjit, I'll just go to the next topic. I think you just think about it. I'll just.
Sir?
So we have special matrices, right? Yesterday, in the last class, we started with the special matrices.
Sir?
In a square matrix, if you take your diagonal elements, you call it as trace. And then now we introduce what is called as a representation.
Excuse me, sir.
Yeah, go ahead.
Sir, what is the meaning of conjugate here? We are using in that A is a conjugate of B.
So this is a mathematical term used. If you conjugate here, what do you mean is
Is it equivalence?
equivalence. Yeah, kind of. Yes, you can bring it down. I think you can correlate that these two. That's what we mean by conjugate. There is a correlation between these two elements.
Okay. Okay.
That's what the actual, I mean, the physical meaning can say. But this we are going to use it for diagonalization of the or block diagonalization of a matrix. If you are given a say 3 by 3 matrix with all the 9 elements are all the characters are all filled up with various numbers, and if you perform this perform the similarity transformation, then it can be converted into a diagonal matrix. And if you can do that, then we say these two, the earlier matrix and the diagonalized matrix, are conjugate to each other. So this is a technique to convert a matrix of 3 by 3 dimension to convert into a diagonal matrix. For that, the similar transformation is used, and in that process, we introduce the term conjugate elements. So a given matrix, we are converting to another form of a matrix. So when we can do that, then these two matrices are called as conjugate to each other. Okay. So, I mean, this is mathematicians use this term. So we are using it. But roughly, it means they are both are correlating. I mean, one form you can convert to another form. So that's why we say it's a conjugate. And only say in C3V point group you have seen only the C3 groups are conjugate. C3 and C32 are conjugate to each other, whereas sigma planes are conjugate to each other. You cannot mix it up. I mean, the C3 cannot become sigma V. There is no correlation. So C3 and C32 are conjugate to each other, and sigma V, one sigma V plane with another sigma V plane are conjugate to each other, but not the axis of symmetry and plane of symmetry. They are not conjugate. They are not. So we separate them into a class. So those elements which are conjugate, so we consider that as one class. So C3 and C32 are one class, and sigma V prime, double prime, triple prime are another class. And identity element we didn't talk about, right? Identity element is class by itself. So in C3V we have 3 classes. One is E, because whatever you do, E will remain as E only. You cannot change it to C3 or sigma V. So C3 is E, identity element as one class. So that is conjugate by itself. So we are not going to change it. Second class is C3. So you can go from C3 to C32. or C3 2 can come to C3. So there is another class, or they are both are conjugate, and sigma planes are conjugate. So we have 3 classes. So yeah, so this is the terminology used by mathematicians where we use for chemical applications. Okay, so that's I hope I answered partially.
Yes, sir.
So representation, we'll talk about this classes or conjugate shortly in detail. So representation, there are 2 types. One is called as reducible representation. And irreducible. Say in a group you have say a few elements E, A, B, C, whatnot, and then if you perform similarity transform, these are in matrix form. E is in matrix form, A is in matrix form, B is in matrix form. And see, all the operations are in matrix form. And if you can perform this operation, say A, take its say Q inverse, and you can convert to another form like A. Now you have chosen A. Okay, so A or E. So whatever. Yes, you take E, you convert to E prime. And similarly, you convert to A in another form, so A prime. Okay, and you're just converting to different form. And say you have a matrix of this one. So basically, what we're trying to do is, if you have a E, we just neglect, but A you consider, and perform a similarity transformation with respect to Q. Then you transform A into A prime. Okay, to do that, say A will convert into A1 prime, then A, this is also A1 prime, A2 prime, then A3 prime, say A4 prime. So like that. Basically what we are trying to do is we are just converting into a block diagonal element. So this is another block diagonal. And then the new A3 will become A3 prime by similar transformation. So what we are trying to do is, if you have a representation of A in a matrix form, say 4x4 matrix. Okay, so A is in a 4x4 matrix, and if you use the operator or symmetry element Q and Q inverse, if you perform a similarity transformation A, then it transforms to A prime. Okay, so this is a complete matrix. A is a matrix, and a form of reducible representation. So you have some matrix of A. A is say something like that, 4x4, something like this. 0, 1, 0, 0, 1, 0, 0, 0. Have 0, 1, 0, 0. So you have something like this, and if you perform some operation using Q and Q inverse, you do this similarity transformation, convert into A matrix into A prime matrix. The new matrix will be all diagonal. So this will be in the form of diagonal element. So you will have here the traces. We'll worry only about the trace. So we try to convert this matrix into block diagonal matrix. Okay. So because all the elements here will be 0. So everything will be 0. So we try to transform the A matrix to A prime matrix. So that process is called as a block diagonalization. So there are elements located here. So this is non-zero, right? So this is non-zero, this is non-zero, non-zero. Off diagonal elements are non-zero. But performing similarity transformation using another symmetry element present in the group, we convert A to A prime. So this is A1 prime, A2 prime, A3 prime, A4 prime. So when you do that, so we are just, what we are doing is block diagonalization. So it's called as block diagonalization. So each block that's diagonalized. It could be 1 by 1 matrix, Like in last example, maybe in last class I was doing, could be 1 by 1 matrix, it could be 2 by 2 matrix, or it could be 3 by 3 matrix. So one can reduce. So this is a reducible representation. We are trying to convert this into irreducible representation. So once you convert it to 1 by 1 matrix, then it is irreducible. You cannot go further smaller one. Say you may ask if you are getting 2 by 2 matrix here, and then perform a similarity transformation, you can reduce it. Some matrices you can convert. This is 4 by 4 matrix, right? By performing certain operations, similarity transformation, this 4 by 4 can be converted into 2 by 2 matrix. Okay, so again you take the 2 by 2 matrix and then perform similarity transformation and see whether it can be brought down to 1 by 1 matrix, all diagonal elements. So if you can do that, so if you can reduce further, so those matrices are called as reducible representation. If you cannot go below certain number, you cannot bring it 0 everywhere. So this is final. So this one cannot perform a diagonalization beyond this. So this representation is called as irreducible representation. So we say if it is this irreducible representation of dimension 1, just 1 by 1 matrix, then we call it as a one-dimensional representation. If it is 2 by 2 matrix, say A1, A2, you can say A11, A22, and say you have A12, and here it is A21. So this is 4 by 4 matrix, diagonal, whereas these are all singly diagonal. So if you choose this and perform a similar transformation, we cannot go further down. Then we say this 2 by 2 matrix is a irreducible representation, and this irreducible representation is of 2-dimensional type. It has a 2-dimensional character. And if you have similarly 3 by 3 matrix, which you cannot bring it down to smaller size, either 2 dimension or 1 dimension, then 3 by 3 matrix is called as a 3-dimensional IR. IR means irreducible representation. So for IR, we use the notation, this one. It's not infrared, but it is irreducible representation of certain dimension. It could be 1 dimension, it could be 2 dimension, and it could be 3 dimension. So it depends on the matrix size. So if it is 1 by 1 matrix, all the elements are 1 by 1 matrix, all the diagonal elements are 1 by 1, then we say it's IR of dimension 1. If it is diagonal elements are 2 by 2 matrix, then it's a IR of 2 dimension. So to give an idea how we connect with this with our chemistry, you know, right? D orbital. Last class also I just stopped it here. D orbitals, you have 5 D orbitals, and this is a reducible representation. So you have 5 orbitals, right? 1, 2, 3, 4, 5. Before breaking down, it will be of same type, D orbitals. But once the ligands approach, then this splits into 2 types, right? So this is T2G and EG. So this is you call it as T2G. Maybe small letter, right? You use small letter, I don't know, I forgot. Maybe small letter, right? So one is EG. Because spectroscope is used, we use, I mean the group theory of spectroscopy, they use T2G. And then here EG we use. The spectroscopy use this terminology, CAPS, T2G and EG. Whereas I think the inorganic guys use T2G and EG. So here, you can see this is all the 3 orbitals. I think D, X, Y, Y, Z, X, right? So these 3 will be having T stands for it's a 3-dimensional nature. It's all degenerate. These 3 orbitals are degenerate. Since 3 orbitals are there, so this is triply degenerate, and triply degenerate means in the matrix form it will be 3 by 3 matrix. Okay, so it will be like this. Whereas EG will be, I think, other 2 orbitals, dz square and d x square minus y square. So that is having 2 orbitals, so it will be a 2-dimensional character. So it will have a 2 by 2 matrix, something like this. The block diagonalized matrix will be 2 by 2 matrix. Whereas the d orbital before the ligand approaches will be 5 by 5 matrix. So here basically there will be 5 by 5 matrix. So A2, you can write whatever is A1, 3, 1, 4, 1, 5. Similarly, you can fill everywhere. Right? There will be 5 rows and 5 columns. So you can fill all the elements. It will be populated. But once you perform similar transformation, this splits into a 3 by 3 matrix, which will have a T2G character, and the remaining will be 2 by 2 matrix having EG character. So like this, orbitals will be split, and then its bonding will be decided by which axis: x-axis, y-axis, z-axis. So like this, we'll split it. So this is triply degenerate, and given by, that's why its symbol is T. If it is doubly degenerate, the symbol is E. And if it is not degenerate, if it is just single generate, then we call it as symbol A. So A or B we use, whereas for doubly degenerate, E is used, and for triply degenerate, T is used. So to convert a matrix of this type, A22, A33, A44, A55, A2535, so A32, A34, A35, so like this, you can fill it other 2 rows, A42, A43, 44, 45. This is for d orbitals, 52, A53, A54, 55. So this is for d orbitals. It will be, this is called as a reducible representation, but performing a similarity transformation, we can convert this 5 by 5 matrix into all diagonal elements. Okay, so you can say this is 0, 0, 0. There will be one more column also. 0, 0, 0, 0, A5 prime. And now we have made it 3 by 3, right? So it will be in 3 by 3 form. So it will be again, so this will be one class and this will be another class. Okay. So this is A, so what, A, B, let's say 3, 3, 4, 4, 5, 5, A, 3, 4 prime, then A, 4, 4 prime, 5, 5, 3, 5, 4, 4, A, 4, 5 prime. This will be non-zero. The other terms will be 0. This will be 4 P prime A 5 3 prime A 5 4 prime. So what we have done is we converted the 5 by 5 matrix into 2 special matrices. So this one is 2 by 2 matrix. This one is 3 by 3 matrix. So we have converted a reducible representation of d orbitals into irreducible representation of d orbitals of 2 by 2 matrix and 3 by 3 matrix. And this one, basically, it is for T2G orbitals, and this is for EG orbitals. So we can correlate like this. Okay. I think what's the time now? I think I'll stop it here. Find some. You are getting some idea what we are trying to do. So we'll see how we are going to work with the d orbitals. Before going to d orbitals, we take simple systems. P orbitals will work. We'll take multiple examples of p orbitals. See how bonding is formed, how IR Ramans are all number of vibrations possible in IR Raman, of which symmetry. Symmetry is important. We find out the symmetry of vibrations. So after doing that, then we'll jump to the d orbitals. Okay. So, but yeah, to understand the representation, I just took a d orbital to convert from reducible representation to irreducible representation. Okay, so I can stop it here. I'll share the scan copy of the notes, which have details of all these things. So we'll continue with this maybe next class. Okay, yeah, I'll stop it here. We'll see more about the representations, notation. Then we go to the character table. So we sum it up the diagonal elements and write character table, which will be handy for prediction of symmetry of various bonding. Okay. So I'll stop the recording.